Good morning, everyone. I am Shurjit. Welcome to Expert Talk. This session is co-organized by IEEE Census Council, Student Chapter, IIT Indore, IIT Council, Student IIT Indore, IEEE Madhya Pradesh Section, Electron Devices Society Chapter. I kindly request all the participants to turn off their videos and keep their microphones muted. As you all know, today is National Science Day, celebrated in honor of Sir C.V. Raman and his groundbreaking discovery of the Raman field of spectroscopy. This day reminds us of the significance of scientific curiosity and innovation in shaping our world. As Sir C.V. Raman believed, science is not about finding the right answers, it is about asking the right questions. With this spirit, we gather here today to celebrate scientific curiosity and knowledge sharing. It is my pleasure to welcome Professor Mahesh Kumar from IIT Jodhpur, who will be sharing his thoughts on machine learning approach to develop real-time prediction model for hydrogen sulfide detection. Here's a brief bio about our speaker, Professor Mahesh Kumar. So, Professor Mahesh Kumar is a professor at Indian Institute of Technology, Jodhpur. He has received INSA Medal for Young Scientist 2014 by Indian National Science Academy, the MRSI Medal 2016 by Material Research Society of India, DAE-Young Achiever Award 2016 by BRNS, Research Excellence Award 2020 by IIT Jodhpur, and Friedrich Wilhelm Bessel Research Prize, Alexander von Humboldt Foundation, Germany. He is recipient of the NAWA ULAM-2024 fellowship by Polish National Agency for Academic Exchange, Brain Pool Program 2022 by Korean National Research Foundation, Fulbright Nehru Academic and Professional Excellence Fellowship 2021, the Royal Society National Exchange Award 2021, JSPS Invitation Fellowship 2021, PIFI Visiting Scientist Fellowship 2021 by Chinese Academy of Science, 2 Officer Fellowship 2020, Bhaskara Advanced Solar Energy Fellowship 2020-2018, and in the INAE awarded him Abdul Kalam Technology Innovation National Fellowship 2022. He is also editorial board member of Nanotechnology, IEEE Census Council, Bulletin of Materials Science, and Nano Express. He is also fellow of Royal Society of Chemistry and Institute of Physics. He is founding member and served as chair of Indian National Young Academy of Sciences. He has published more than 200 research articles. His research interests focused on 2D materials, nanomaterials, sensors, semiconductor materials, and devices. Now I would like to hand over the mic to you, sir. Sir, the stage is all yours. You may begin.
Yeah, thank you. Thank you.
Thank you.
Thank you so much. Let me share my slides. Can you see my slides?
Yes, now, sir.
Okay. Yeah, thank you. So very good morning to all the this one participants, and today I am going to talk about this one, how we can use the machine learning to predict the exact concentration of any gas. And today we are taking the example, this one is the H2S, but similarly you can make for the other gases as per requirement is there. And what is the role of machine learning? Why do you need this one machine learning? Why our sensors is not giving the exact this one data, particularly the exact prediction value is there. So today in today's lecture we are going to talk all about basically how machine learning approach or AI is there, particularly that is helping in developing these teeny sensors here. So we can basically we can monitor this gas environment or wherever we are using this one. So at IIT Jodhpur, our research group is mainly focused on the material synthesis. We synthesize the different materials, 2D materials, metal oxides. Also, we work on the 3-5 semiconductors, mainly on the aluminum gallium nitride and gallium nitride high electron mobility transistors. And all these basically materials we use for the different type of the devices. We make basically gas sensors, we make heavy metal ion sensors, we work on this one dosimeters, radiation and photodetectors. Also, we have started some work basically by using AI and ML, how we can improve these sensors performance basically, because in AI, main AI or IoT, the main this one component of this complete this technology is the sensors. So how we can make basically these compact sensors and then we can get the exact data. So today I have taken the one example that is the H2S gas. So H2S gas basically emission is happening when food decompose this one. So many times this one we have seen in the media basically there are the casualties because of this high concentration of H2S. Mainly this is happening in the garbage, even septic tank or sewer lines. So wherever basically these food components are there, when they are decomposing this one, H2S emission is there. And we have to monitor basically how much emission is there. Otherwise, one thing we are disturbing the environment, and another this risk is there because if some blockage or some other type of this repair is required, when these labors they are going inside these sewer lines, because of the high concentration, their health is on the risk here. Another application is in the oil industry. It's okay when they are basically getting these crude oils. Before this one, H2S gas is always present. This one, so now we can measure exactly these gases by using the gas chromatograph is there. But gas chromatography cost is around 15 to 20 lakh. Also, basically, this will not work in the environment. We have to collect some samples and then we have to do the analyze this. So if we have some type of the basically sensors that can work on the environment, or you can say in any environment, and cost is another this one very important factor is there here. So if you can make basically low cost these sensors here, we can mount basically in the sewer lines, we can monitor how emission is happening somewhere, basically H2 emission or this ammonia and methane emission is very high. That means particularly in that region some blockage is there. So we can basically we can monitor the sewer lines using these sensors. So if you make any type of the sensors, these are the basic parameters basically. Those are important here to understand here. So these are the basic characteristics. This one, we need the material should give the high, this particularly the response is that response should be high here. So first we have to, whatever quantity we are measuring the resistance, capacitance or any other parameters here. Particularly this resistance is that this change in the quantity we call the sensing response is that should be high. Stability in humid environment, stability with temperature, because mostly these gas sensors they are working at higher temperature. This one 200, 300, this one depending on the materials. But again, the power consumption is high, this one, because we have to maintain these sensors at those high temperature. So if you can develop the low temperature basically here, room temperature, these sensors, so low temperature, in that case, we can save the power here. Response should be fast. Okay, within few seconds, basically, we should get the whenever some leakage or if you want to use within a few seconds, we should get the response. Again, the cost and this power consumption, these are the other factors here. So by considering all these factors, basically, how we can develop this high sensitivity and high responsivity based sensors here. So your sensitivity should be high. Again, another parameter is the selectivity. So here today we are going to discuss all these parameters basically by using or by keeping in mind all these parameters, how we can develop this really high quality sensors. So now here, if we are making any type of the sensors, as we try to understand basically what is the physical or chemical phenomena is there. Based on these phenomena here, we can make the different type of the sensors we can develop here. So here these sensors basically as compared to the other method is there, as I said, the gas chromatography is there, but cost is very high here. We can make here the working principle is very simple. This is the conductivity based is there. So there are few materials, basically your metal oxide or 2D material or another class of the materials. These materials, when we are exposing in a particular gas, basically in that case charge transfer is happening, this one, or on the surface some phenomena is happening, and because of this phenomena, what is happening here, resistance is changing, this one. So we can monitor the basically conductivity of these sensors, how this conductivity in different concentration of particular targeted gas, how conductivity is changing, we can calibrate and then we can make this one, we can make these sensors here. So today my focus is that is on the chemiresistive sensor here. So how we can develop the chemiresistive sensors, and then these chemiresistive sensors we can integrate basically with some IoT platform, and we can use the machine learning algorithm to predict the accurate value of these gases. So metal oxide based here, the first sensor was developed in 1960 by, we also call the Taguchi sensor is there, by the Japanese scientists. So here in 1960 they have developed this one, they have used a metal oxide here, and now the metal oxide, when we are exposing in a particular gas, this metal oxide's resistance is changing. And after that, this one different these metal oxides were used for the different gases. For example, zinc oxide is generally used for the hydrogen sensing, TiO2, WO3, SNO2, and there are many more basically. These are explored for the different gases here. But here, what is the working principle is there here, particularly because these sensors are working at higher temperature. So here we can use basically one nichrome heater. This is also called the Taguchi sensor is there. He used basically one ceramic tube, alumina tube, and inside the tube we can use the nichrome heater here, and outside we can take the two contacts, and now these materials here we can apply the constant voltage, and now how resistance is changing these materials when we are exposing in the different concentration of the gas. We can reduce the operating temperature. We can reduce the operating temperature basically here by using the nanomaterials. Also by making the micro heaters, MEMS-based heaters here, we can play with the operating temperature and we can reduce the power consumption. But what is the problem, this one? The major problem in the metal oxide based sensors is the baseline stability. That means here, when we are exposing this one, before exposing, here you, hello? Yes, any?
Yes, sir, you're audible, sir.
Okay. If you have any question or something, this one, you can stop me and you can ask me. That will be easy for me, this one, to answer on the same slide. Okay, so
No,
the main issue is... Okay, thank you. So the main issue is there, that is the baseline stability. Baseline stability means initially your material, some resistance is there, and when we are exposing in the gas, now resistance is increasing or decreasing. That is depending on the mechanism. We are going to discuss this one. Particularly here, what is happening? Once we remove the gas, our sensors should come in the initial position. Suppose this is the initial resistance is there. We are exposing, here resistance is changing, and now if you are removing the gas, here particularly this line is not coming, here resistance is not coming in the initial stage. So this is called the baseline stability is there. And if you are not getting, basically now is very difficult to predict the accurate concentration. Another one is that here metal oxides, they are affected by the low sensitivity and selectivity, sensitive to environmental factors, as I said, this one, humidity and temperature, because if you are doing the measurement in Srinagar or Rajasthan, basically, there is a temperature difference is there. Again, the humidity difference is there. So these sensors performance should not be affected by the environmental factors. Operating temperature is high. This one generally is above 150 degrees centigrade. And because of this high temperature, the power consumption is there. That is the very high is there. So how to come all over these drawbacks basically here, how we can use the machine learning here, and then we can basically minimize all these negative points. So first, I will try to explain basically what is the sensing mechanism is there. Why these particular few materials, basically, they are selective towards basically a particular gas here. So we can understand this one. I think all of you know this one, how diode is working or how PN junction is forming. So in the PN junction, we are taking the P-type material and N-type semiconductor materials. In the P-type, your Fermi level is close to the valence band. Here, Fermi level is close to the conduction band is there. And now, if you join both material, what will happen this one? When we are joining, basically when we make contact of these materials, now in the P-type materials, holes are majority carriers. Here, electrons are majority carriers. So these carriers will start moving from higher concentration to lower concentration. So holes will move from P-type to N-type, and electrons will, this one, diffuse from N-type to P-type. And here what is happening, this is at t equal to 0 time. When we are going higher time, t equal to t1, here, now particularly in this region, these electrons and holes are depleted, and they are leaving behind the immobile ions. So here positive means basically these are the ions here. So electrons basically they diffused from N-type to P-type, and here is leaving the, here particularly your immobile charges. So in the steady state here, what we will get the electric field is there here basically, and now this electric field is there. This will stop basically the further here diffusion of electrons from N-type to P-type and holes from P-type to N-type here. So this will stop here because of the concentration, holes will move in this direction. But because of electric field here, what will happen, this one, holes will go back. So we call this is the steady state is there. In this region, now your carriers are free carriers that we call the electron and hole, both are depleted. And now what is happening in a diode, we are making the contact here, and now we are applying the voltage here. So now that one direction, in the forward direction, we will get the current, and reverse direction, current is almost negligible is there, very small current is there. So this is the, here your diode working principle is there, how particularly this diode is working here. So now this region is completely depleted region. That's why we call this is the depletion region is there. So to understand the gas sensors here performance, basically we can use the same this working principle here, and then we can explain basically how gas sensors are working. So now suppose if we consider here, if we consider a semiconductor material. Suppose this is the N-type semiconductor material is there. And now here on this N-type semiconductor material, if you make the contact from top and bottom here, now how much will be the resistance by Ohm's law? We can calculate. We know R equal to rho upon L is L upon A is there. So L is the width between both both electrodes, how much your length is there. A is the area of this one here, your contact area, how much is there, top and bottom, your contact area is there. And by using this one, we can calculate. So now suppose we are not changing any doping this one. So rho is the material property is there, your resistivity is the material property is there. And now if you want to increase, for example, resistance, what we have to do, because material property is constant, L we can increase, or by playing with basically length and playing with the contact area as per our requirement, we can tune the resistance here. So this is the simple here. Ohm's law is there. By using this concept, basically we can measure the resistance here in unknown material. This one, if resistivity is known, we can calculate basically here how much this one resistance is there. Now you try to understand this one. Suppose we bring, hypothetically, if we bring a p-type semiconductor near to this one. So here particularly this is the N-type, here our semiconductor is there. Now we are trying to bring here a hypothetical p-type material is there. So if you bring the p-type material, what will happen? Here again depletion region will form. So electrons will diffuse from N to P and holes will diffuse from P to N here. And now when they are diffusing, now what is the yes, please. If you have any doubt. Okay. Now what is the impact particularly on the resistance of this material? What will be the impact? Because in this case, that area is there because electrons cannot move from this region. Electrons cannot move because there are no free electrons. So in this case, what will happen? Our cross-section area is there. This is decreased. This cross-section area is now A minus del A, and del A is there. This here depletion width is there. This is decided by the here p-type doping. What is the p-type doping is there? If this is highly doped or if this is lighter doped or moderate, accordingly here this one your cross-section area del A is there. Here this del A is there. This will vary particularly. So to understand the gas sensor's working principle, we can assume this one here, this p-type material is there. This is a one gas molecule is there. So one gas molecule is coming. Suppose this molecule is taking the electron. What will happen? Our cross-section area will decrease because here depletion region will form basically. So if these gas molecules, if they are taking the electron, what will happen? This depletion region is there, this will modulate. So suppose more number of electrons, this one gas molecules are there, here depletion width will be the larger and there will be a saturation. So up to a certain concentration, basically our sensitivity or change in the resistance that will increase. Okay, change in the resistance will increase, and then what will happen? We will get this one saturation. So now here our resistance is there. Particularly, we can say this is the function of the p-type here concentration or how many number of molecules are coming. So now the change in the resistance is there is function of the gas molecules. So this is the here if you take any type of the gas sensor, this is the working principle is there. By using the semiconductor here, basically PN junction, we can explain particularly how these gas sensors are working. Now I will come on this one. Suppose here you can see this is the conduction channel is there. This is for the hydrogen case is there. So suppose if you take the material and initially from the environment oxygen is absorbing oxygen, that means oxygen is taking electrons from the material, and we will get a less, this conduction channel is there. And now suppose if you expose in the hydrogen, hydrogen and oxygen both are reacting and making H2O, and whatever electron these oxygen atoms, molecules they have taken is giving back. So now the conduction region or conduction region is that this area is increasing. So in this case here conduction was less, now it's high. So your conductivity is depending on the here conduction channel or how conduction channel is modulating. So here if radius here or diameter is higher, conductivity is higher here, or if diameter is less, conductivity is lower. So accordingly, basically, we can monitor here how many number of molecules are coming. So in this case, because in the environment we have the oxygen, so already this material is absorbing the oxygen molecules. Oxygen molecule is taking electron from the materials and making the depletion region. But when this reaction is happening, basically, again, this giving back this electron to the semiconductor, and now there is a change basically in the resistance. We can monitor this change, and then we can make these, particularly these gas sensors. So this is the conventional approach is there, where we are measuring the resistance here, and then so this is the conventional approach is there, where we are measuring the resistance, and then we are monitoring basically how much percentage of this particular gas is there. So here conventional approach is there, when we are exposing, resistance is changing. And now once we remove this gas, our sensor should come in the initial stage. But practically this is not happening, this one here. So in the conventional here approach, what is the issue is there, when this baseline is not coming in the initial stage, there is an issue of baseline stability, non-linear responses, poor stability, signal fluctuation, cross-selectivity, humidity. Particularly, basically, these are the drawbacks basically, and we are not getting the exactly the actual concentration, how much in the environment actual concentration is that. So what we have done, we have approached a new approach. We call basically this is the new approach, where we are measuring the impedance, plus we are applying the machine learning. And by using this one, we can overcome this baseline stability and other drawbacks. Basically, we get the linear response, broad dynamic range, here baseline stability, and environmental factor also affecting the minimum here. So what is this new approach here, where we are measuring the impedance? Here we are measuring only the resistance, not the impedance. Here in the impedance means basically we are also measuring how much capacitance is there, how much resistance is there at different frequencies. We are doing basically these measurements, and then particularly here, we are applying the machine learning algorithm by considering all these parameters, and we get the better results as compared to the resistance. So first we try to understand here what is the impedance, or what is the need to measure the impedance here. Well, here, because if we can get the data from the resistance, why do we measure the here impedance? So this is the mechanism, as already I explained. This one here is if this is the n-type semiconductor is there, now depending on your oxidizing gas or reducing gas is there. So taking electron or giving electron, based on this one, your electron depletion layer is there. Particularly this will module, here modulation will be there. Now the change in the resistance is depending on this gas concentration. Similarly, suppose p-type semiconductor is there, then we call basically whole accumulation layer is there. So it's similar. In this case, here the conductivity is higher of the accumulation layer. So accordingly, basically we will get, but here behavior will be in opposite direction. So what we are doing this one, if we try to understand from the materials prospect this one, we are making a electrode, then we have, for example, nanomaterials we are using this one. So on the top here, we have the depletion region. Inside this one, we have our pure semiconductor materials. What we are getting, one is this one contact between electrode, this one electrode contact, and another these contacts are we call the interconnect is there. And because of this one, what we are getting here, we are getting the additional resistance because of the interconnect here, or material your resistance is there. One is between electrode and your material. If this is ohmic, so key, but we are getting some contact we are getting. Now, how here you can from this diagram you can understand basically how electron flow is there here. So the electron flow is depending on the shortest path, and then we get the current flow is there basically. So this is our current flow is there here. Now here there are two important parameters. One is as I said, that this RC is the contact resistance, RG is basically your from the material. This one is coming, how much is there, and another one is coming from the bulk resistance is there. So this is the bulk resistance. This is from the grain. Your interconnect is there here, and another one is your contact resistance is there. So only when we are doing resistance measurement, we are measuring only on resistance, and we are ignoring basically the capacitance. Okay, that capacitance is coming either from the contact electrode or it's coming from your grains basically. But here in the impedance measurements here, we are considering all the factors. We are measuring resistance also. We are measuring basically here, we are measuring capacitance also, because impedance is giving the overall effect of these your capacitance and resistance. How to measure this one? So resistance is simple. Basically, we can measure, we can apply the constant voltage and current, the ratio we can calculate. But to measure this one, impedance either your capacitance or inductance is there, we required the AC signal we required. And here one more basically parameter is coming, that is the phase here. How much is the phase difference is there between your current and voltage here? Is this one is leading, or this one is basically behind, depending on which parameters, which basically component we are using. So mainly our focus is there basically that is only on the capacitance, because inductance we don't have here, this one. And again, is your capacitance or inductance or impedance, this is also depending on the frequency here, which our signal frequency or measurement frequency, what frequency we are using this one. So what we have done this one, we have done measurement at different frequencies, and then we collected the data, and all this data we put in the machine learning this one here, and then our output is getting that is more this one closer to the actual values this one as compared to the resistance. How to measure this one? So this is the simple resistance measurement is there. We can apply a constant voltage, and then we can measure this current, and then from ratio we can calculate how much this component resistance is there. This is applying basically your DC bias. If you are applying the AC, similarly we can calculate this one. But in the resistance, basically, your both here current and voltage, they are in the same phase. There is no changes there in the phase here. But when we consider the resistance here, the phase is also coming. There is this one in the capacitance here. Your current and voltage both are not in the same phase. This one, there is a delay is there. And we have considered also this phase also, basically how this phase change is there in the presence of gas and in the absence of the gas. So here one more this parameter is there. This is the capacitive reactance is there. Otherwise in the resistance here we can apply the DC bias, and from DC we can calculate here particularly how much change is there in the resistance. But in the capacitance, if we are measuring basically, one is frequency here, we can vary the frequency. Another here, we can also measure the phase, basically your how much change is there in the phase, and that also we can relate basically with the sensing. We grow this one a different type of the metal oxides, this one here. So this is the one example is there for H2S. We have deposited the tin oxide, and what we found basically tin oxide is giving the good sensitivity towards the H2S here, but this is not selective. So then, okay, we have deposited some copper oxide, this one decorated, and copper oxide is having another problem, this one. If you are using pure copper oxide, because H2S is there and we are doing the measurement at 150 degrees centigrade. So copper oxide is converting from copper oxide to copper sulfide, and copper sulfide is highly conducting, and that is not giving any sensing towards the H2S. So that is the issue. Because of this one, we have only decorated here by using the copper oxide, but our main material is the tin oxide is there. We deposit by sputtering. This is our device here. You can see these are the deposition parameters here, and particularly this is our sensing device is there. So we can take the contact from here and then we can do the measurement. So what we do this one, first we deposit these materials on the simple silicon wafers basically, and then we do the all processing. And once we finalized, okay, this is giving the best parameter, then we deposit on alumina, because here we are using the external heater. So in our setup, measurement setup, we have the heater. So as per required, this one, as per requirement, we can vary the temperature, different temperature, and then particularly we can do all these measurements. But to make a prototype, basically we deposit this one on the silica tube, and then we make the heater. So here these are the material. This one characterizations by XRD, we confirmed this one is the tin oxide. Also, when we have decorated copper oxide for 60 seconds, we got a small hump. Also by EDEX and XPS, we have confirmed this one. There is a deposition of, because this is only 60 seconds. So the copper oxide thickness is very small. So in XRD, we are not getting this one, this high peak, because thickness is not sufficient to get the signal from copper oxide. This is this one pristine sample. You can see basically at different concentration, this is giving a very nice change in the resistance here. And when we have here is the relative response is there. That means we are calculating our resistance in particularly in gas minus in air upon RA. So from this we can calculate basically how much we define. We call this is the particularly relative response is there. Yes, Vishal, you can ask. You can unmute and ask if you have any doubt.
Sorry, Mahesh sir. In the last slide, I wanted to ask in the impedance measurement, what is before and after? Is it before exposure and after exposure?
Which one?
Last slide, previous one.
This?
Where you mentioned about impedance.
Yeah.
Yes.
Yeah, I will come on this one. It's depending on the capacitance, how much is there. This is the simple, basically, how we are measuring the capacitance. On the sensor, this is not measured.
So
I will come
on.
Yes. This is the simple. Basically, what is the phase?
Hello, participants. We will have a Q&A session after the talk, after sir finishes his talk. Okay.
Okay. So then we have decorated with the copper oxide for 15 seconds, and the response is there. You can see this one is coming 60 now, slightly is increasing. This one again we have done basically for 30 seconds. This is increased 70%, 45 again. So basically, if you see this response value is there, this is increasing with decoration. and then 60 second we reached close to the 70. And again, if you are doing higher this one, then this is particularly is decreased. So here we have stopped this one. 60 second of decoration, this is giving the improvement basically is from 60 to 70, 10% improvement is there in the sensing response. But more than this one here, if you check the selectivity, this sensor is not selective because ammonia and this is giving almost here not much change is there if you are taking the 50 ppm and if you do the measurement. But after here 15-second decoration, some improvement is there, but not great here. Again is increasing here, the response is increasing from 58 to now 62. And finally basically if we check this one, here we are getting in the 60 seconds, basically these are below 10 and this is close to 70%, 65% is there. So just by decorating some metal particles or this copper oxide, we can improve the sensor sensitivity here. So here we can improve basically, here you can see all together this one. So particularly the 60 seconds here decoration is giving the highest sensitivity. Now the another question why we have not done only copper oxide, because you can see this is switching from copper oxide to the copper sulfide, and now the conductivity is very high. So now the change is almost negligible change is there in the current when we are using the different ppm here. So that is the reason, because copper oxide is reacting with H2S and making the copper sulfide and H2O basically. Because of this one, we have not used. We have explored many materials. I will not go through all the materials, but I will take one. This is the copper chromium oxide is there, is giving the very good response. And then again, we have decorated with the PD. So here you see the resistance, how this is decreasing, that is in the semiconductor obvious, when we are increasing the temperature, resistance is decreasing. This is the sensing response is there, and the here issue is the here your baseline stability is there. Also, this is depending on the decoration is there here. But we got the maximum here. I think we got in the 9 second, we got the maximum change is there here. So basically, we got the maximum change. Then we have done the material characterizations here, XPS, XRD, and we have confirmed basically there is this PD decoration is there here. And what type of this one, some oxide is forming, some pure here PD is there. In only just for 9 seconds, we have to do the decoration. And the thickness is around 200 nanometer is there. And this is the very nice, basically rice grain is there, because here gas sensing is the here surface phenomena is there. And now if you can increase the surface area basically by making these nanos, basically overall our sensors performance will be better. What we have done here, we have done basically with PD, and we found the response is very high. Just when we almost double is there when we are decorating with the PD nanoparticles, is giving very good stability in different ppm. Here you can see this one, even we can measure here around 500 ppb to we have done this one around 1% H2S gas here. So there is this one change is there, almost this is the linear. So our transfer function is coming, change in the response and concentration is almost linear is there. These are the other parameters, selectivity. This is the highly selective is there. Again, the response time is around 35 seconds. But again, second time, if you want to use, we have to wait for the 3 minutes, around 180 seconds. In the gas sensors, this is acceptable. And these are the other, this one in the humidity, other performance parameter is there. And next, what we have done basically, then we have transferred this one on a prototype here on the alumina tube, and then we have performed all these parameters, and we found basically this is highly selective towards the H2S is there. So how we are doing basically here, this transformation in the sputtering, we use this alumina tube, and then we do the deposition. Basically here you can see is we do the deposition in the sputtering, whatever thickness we have deposited on SiO2, we have optimized same here thickness we are using. All other parameters are same. So you can see here we are depositing basically these particularly these material copper chromium oxide, and then we check the heater. So our temperature we keep around 150 C. So by this buck booster converter, basically we apply the constant voltage for the heater. This is our sensing setup is there, very small setup is there, and then by the impedance, this is the circuit. By using that we can record the impedance. And so these are the two airtight boxes are there here. So from this side gas is coming, here is our sensor, and then another this gas is going out basically, and then here we measure the impedance. So particularly this is the schematic diagram is the same whatever I have showed. This is after deposition. You can see here we have the cylinders. By MFC we control their flow of these different gases, and then we measure the impedance. So here the impedance is, you can see, is the function of the frequency, also depending on the different ppm. So here is from 0 to we have used this one 16 ppm, and in different ppm basically now the impedance is depending on the concentration of the gas. Again we have this one measure the real part, and we have measured the particularly this is the imaginary part. We have measured also the phase. So here with frequency basically this is varying. If you are taking higher frequency, lower frequency, here the change in the impedance is changing, but in the change in the phase is almost constant with the frequency. So we can use also the phase. We can measure the phase only, and then we get the information how much concentration is there. This is the simple. Again, our real part and the imaginary part basically we can plot, and from that also we can make out how much percentage of this gas concentration is there. So next what we have done, we have recorded all this data. So we can consider basically the impedance here at 100 Hertz is there. This we can consider as a DC signal is there. So after one cycle, second cycle, here the baseline is there, that is not stable. Clearly we can see from this black diagram is this black dotted data is there. Basically this is the at lower frequency, that means we are measuring only the resistance. But if we are going higher around 10K, basically our baseline is stable. Now in this case the baseline is almost stable is there. So if you measure at 10K frequency, basically we are getting the stable data here. And phase is stable, phase even lower frequency also it is stable. This is giving more this one accurate value than the resistance is there. So all of these parameters we have measured, and then we have used in the machine learning. So here we are using basically this artificial neural network here. So we put all these parameters, frequency, humidity, phase, all these we give as an input, and our output is that is the here prediction of exact how much value is there. Here H2S is there. So we have this one taken data collected at 0 and 20. This one 20% of humidity was used for the training, and this data was divided in 80 and 20 for training and testing purpose. So 80% data we have used for the training and 20% we have used for testing. So well-trained model was same for the prediction. So we have used for activation function, particularly these tools optimizer, again epoch, this one 100 to 200, and this is the mean square, this one error is there, that should be the minimum. So first we have optimized all these parameters. So here you can see for each of this one we have optimized this one. This is the particularly the mean square error is there. We try to minimize as possible. And then we have done this one here in the pink color is the actual, and these are the measured values are there. And these are the basically here actual value and predicted value is there. Here we have used only the single frequency around 10K, and then we have predicted, and we are close this one here. We are closer to the actual values. Next, what we have done here also, we have used the different models. This one, first we have considered only the single frequency. In the single frequency, only problem is that in the first cycle, we are not getting closer to this one, because there is a variation is there. Heater is also taking some time to basically give the stable temperature, and we are getting the deviation some in all parameters, either in impedance, phase, or your real part and imaginary part is there. Next, what we have done, this one, we have used the multi-frequency model. Also, we have used the humidity. So 0% and 20% we have used for the training and testing. And these values basically we have predicted, and we are getting closer to the basically actual values here. So predicted values in black, these are almost close to the actual concentration is there here. So this we are using only impedance. Here we are using phase particularly, and in this case we have the real part and imaginary part is there. So almost here we are reaching basically closer to the actual value. Also the baseline stability issue is there, that is also resolved by using this machine learning NN model. And here we are using lot of data at different frequency. We are using humidity, we are using, also we are considering now phase, impedance, a real part, imaginary part. All these we are putting in the NN model, and we are optimizing basically these data. So here you can see in the 40% environment, here we got the 40% RH environment. This is the phase basically. This is the other impedance parameter. Here is the phase. So as compared to the other, phase is giving more accurate value basically, how phase is changing basically in the different concentration. This is giving more accurate value as compared to the other parameters. But if we consider all parameters and then if we put in the NN model, we are getting the more closer way to actual values. Another parameter is this one important here, sensors performance parameter is how much is the cross selectivity is there. So we have used H2S, we have mixed with NO2, ammonia, methane, because in the civil lines, these are the other gases, generally they are available basically, or particularly the combination is there. And now we have done the phase shift, and phase shift we got basically here more closer this one. And if we see basically our prediction value, actual value is the 10 ppm. With 10 ppm, we have mixed the other gases here. So other gases, CO2 is 100 ppm, NO2, this one. In 10 ppm of H2SO, we have taken higher concentration of the other gases basically, and then we have mixed. And almost our model is giving the value that is close to 10 plus minus 1% or 2% is there particularly, but we are getting very close to the actual values. This work is done by my PhD student Amit, and machine learning part was done by the Bharat basically. He is helping us this one, and I would like to thank Abdul Kalam, this Technology Innovation National Fellowship, for supporting us for particularly this work. So thank you, and now if you have any question, you can ask me.
Thank you, sir, for such an insightful and enlightening session. The floor is now open for question and answers. Participants, you may raise your hand, and then I will call you one by one. Okay, and while you are asking the questions, please switch on your videos. Yes, Vishal Bardi, please switch on your video and ask the question.
Yeah, good morning, Mahesh sir. First of all, thank you for an excellent talk. So I just want to know, like you mentioned, you are using silicon as a deposition substrate, right? So will it not affect the resistance or impedance in any way, because it's also has some resistance associated with it?
Yeah. So what we are doing, because initially we have taken the silicon, but this impedance data is there. All these are taken on the prototype sensor. So alumina tube is there. But again, I will come on this one, how basically this resistance is not affecting. So what we are doing, our material is the N-type material is there. So we are taking the P-type silicon. So now the current flow is not towards the P-type. So you can take in opposite direction or better, because is depending on the growth condition also. Sometimes you cannot grow the on-oxide samples. So if your material is P-type, you can take N-type. So that will be the PN junction will be there. So now your conduction will not be through the substrate.
Fine.
Okay.
And yeah, got it, sir. One more question regarding that impedance measurement you were showing, na? Before and after was what I couldn't get that actually
So
on one of your slide.
Yeah, initially that is the basically phase is there. How much this difference is there between your current and, because this is the your sinusoidal wave is there. So how much if both are at the same, for example, in the resistance both will come current and voltage. If current is increasing, voltage is also increasing. But in capacitance, this is not happening. There is a phase lag is there before.
Yes.
So that is the phase, how basically this phase difference is changing with different concentration. So that slide was only to explain what is the phase lag is there. But after this one, I have showed this one, your phase is increasing or decreasing. That is particularly with gas, how that is increasing, how that is decreasing once we are removing the gas. That means we have taken the phase initially without gas, how much phase is there. Now suppose that is this one 60 degrees there is going 60 to 70 degree is coming 60 degree. So that is at different concentration how that is changing.
Okay. And one last question, Mahesh sir, regarding this, you have used machine learning, right? So what can you comment on the accuracy and precision of your model? Like,
okay, so basically this is only for the baseline stability, because that is the major issue there. Okay. So because accuracy, this is also depending how many epochs we are taking this one. So we have taken close to 80 this one. So because your calculation time is also depending this. So in 80 we are getting closer to our actual value is there.
Okay, thank you so much.
Yeah.
Yes, Mr. Brahmadat Mahapatra, you please switch on your video and we make my solution.
Thank you so much, sir, for the great talk. All the sensors have different base resistance value. So how do they give the same response for a particular gas concentration or not? If yes, then how it is possible?
Yes. As I said, resistance is depending on your size and also depending on the material. This one initially I have showed you this one in my initial few slides, this one. So particularly the response we have defined. That means initially how much resistance is there in the air, and when we are exposing with the gas, how much is there. So response is generally the change in the resistance in particular gas, and is the Rg minus Ra on Ra. So Ra is there, basically this is the resistance in air. So if your resistance is high or lower is there, this will be only the difference we are measuring.
Okay, sir, if the two sensors have different base resistance, so they give the same change in resistance for the same concentration of gas or no?
Change should be same basically. If you are using same material, this one, your change will be the same.
Okay, sir. Sir,
if you are crossing the quantum limit, that might be different. Otherwise, if you are going, for example, in one sensor, if you are keeping your 100 micron, another you are keeping 50 micron, your base resistance only will be different, but your change in the response will be same.
Okay, sir. Sir, how can we confirm the selectivity for a target gas in the presence of other gases?
Okay, that we do the lot of DFT calculations also, because many, as I said, metal oxides, they are not selective, this one. So there are various ways basically as we have decorated with the metal particles. So that is called the spillover effect, is that they are helping basically these gas molecules to decompose here. Okay, decompose, or the adsorption sites we can increase. So there are various ways you can decorate with some materials, basically some metal particles. You can make the heterojunctions. Again, you can do the doping basically. So there are various ways basically by using that you can improve.
Okay, thank you so much.
Yeah. Any other?
Professor, I have a question.
Yeah.
Actually, H2S is a resistive sensor, right, sir? So what is the effect of self-heating effects? Have you considered the self-heating effects?
That is almost negligible because we are applying 1 or 2 volt, not very high volt. And
Okay.
overall, okay, your dimension is very large.
Okay.
Okay. Self-heating is coming when we are making only the nanometer, very thin is there. Then definitely the self-heating effect is there, but here is negligible.
Okay. Okay. So, Professor, one more question. What kind of ML algorithm has been used in the model?
We have used the ANN basically.
Okay.
ANN
Also,
we have
what
used.
type of training algorithm used?
I have showed this one in my slides. Basically, we have used different modules to optimize these parameters. Basically,
Okay.
you can go through my paper for this one full details.
Sure,
That
sir.
is in the sensor and actuators we recently came, because this ML part is done by our collaborators.
Okay.
So they use that. These are all are the free modules.
Fine.
Yeah.
Thank you. Thank you very much.
Yes.
Mute. Let's say actually he has
Yes, please go ahead.
Hello. Hello.
Yeah. So
Hello, sir.
Anyone can help me this one? What is your question? Yeah, please
hello,
go ahead.
Manish, you may ask your question.
Okay. Sir, I noticed that you are using H2S, NO2, ammonia, methane, H2 and CO2 for the selectivity test.
Yeah.
And while H2S, ammonia, CH4 or CO2H2 are reducing gases, NO2 is oxidizing gas, but the resistance is decreasing for all the gases.
Resistance?
Whether it is
No,
resistance or impedance, it is.
that we are measuring the basically impedance.
Sir, if it for N type or the resistance increase or decrease depending on the N type material, P type material, or oxidizing gas or reducing gases. So if it is
that
the
is
material is N type and the gas is reducing gas, then it should be reducing, and for oxidizing gas, should be increasing.
Yeah, but we have not
But in your
here is total impedance is coming. On the last slide, you are talking about this one. No, where we have measured the impedance, basically your capacitance effect is also coming in that.
okay, the impedance will decrease for all, whatever type whatever the type of gases are.
Yes. That is the overall positive, na?
Okay, and in the resistance, I haven't noticed in the resistance graph.
Yeah, resistance is depending, because oxidizing or reducing is there, that will increase or decrease. Sometimes humidity effect is also coming this one.
Okay.
Okay.
The
So
second
if
one,
you,
so while okay,
because whatever
so while
sensor we are-
depositing, yes sir, yes sir, yes sir.
yeah, whatever basically this one. Basically, we have used where this is only sensing towards the H2S. Other sensing response is almost negligible in there.
Okay. And second question is, sir, while depositing SiO2 and C copper oxide through sputtering, you have used tin target for SiO2 and copper target for Cu or Cu or SiO2 as a target?
So we have used this SiO2 target. We have done by RF sputter.
Okay.
Yeah, we are not doing by
Uh-huh.
reactive.
Means there are two methods. One can use tin metal and then in oxygen environment, one can use SiO2 as a target.
Yes, yes. So we are doing by RF
Okay, sir.
sputter. We are making the target and then.
Yes. Okay, okay. Thank you, sir.
Good afternoon, sir.
Okay. Yeah, good afternoon.
I'm Ramadat Mahapatra, PhD student under Professor Sehwal, sir. And I would like to thank you for accepting our invitation. And I just have a message from Professor Sehwal because he has an invigilation duty from 10. So he sent his regard and said that he couldn't attend your talk. So that's what I wanted to convey, sir.
Yeah, thank you all.
Yes, sir.
Yeah.
And are there any more questions or?
Yes, I have one. Mahesh sir, in this measurement, are you doing in-plane measurement or out-of-plane measurement? Like
this is in plane.
In-plane only. So, so then, like I'm not getting like
yeah.
how your substrate is coming into picture if it is in-plane measurement.
No, substrate is not coming. Basically, if you see in the copper chromium oxide, we have used SiO2, but in the rest we have used the silicon. How is coming? Because if your current PN junction is there, suppose this is on the forward direction is there, another will be reverse bias. So current will not flow through this.
Okay.
Yeah, you can go through our one paper where we have studied only this effect basically.
Okay. Sure.
That is the APL paper is there on the hydrogen on zinc oxide, and the first author is Sapna Ranua is there. In 14-15 we have done complete study on this one because you are taking, there are two diodes. One is in forward bias, another one is in reverse bias. Now you tell me how much will be the current. Suppose this is here, one diode is here, another one is here, is there. One is in forward bias, one is in reverse bias. How much current will be there overall?
Only from the forward bias, whatever is there, right?
No, not forward bias, because both are in the series. So you will not get any current. Yeah, both are in the series.
Okay.
Fine.
So thank you, sir.
Yeah. If you change the biasing also, this will come in forward bias, this will go in reverse bias. You will not get any current.
Okay. Sure, sir. I'll check your paper as well. Thank you so much.
Okay. Yeah, thank you all.
Thank you very much, sir. Due to certain time constraints, we need to end this Q&A session now. Just a minute, sir. Thank you, sir. We're grateful for the time and effort you took to share videos with our IEEE community. Thank you very much, sir. Fine.
Yeah, thank you.
I'd like to thank, I will end this session by thanking our IEEE societies and our supervisor, Professor Shaibal Mukherjee, for encouraging us to organize this type of events and the entire team involved in making this event a grand success. Thank you very much, sir. Thank you, everyone. Have a nice day.